Good evening, class.
Good evening, sir.
Mm-hmm.
Good evening, sir.
Yeah,
Good evening, sir.
in the lecture. The lecture is supposed to start at 5:10. Okay, so you take notes
Okay, sir.
of that.
Okay, sir.
Okay, good. Also, I realized that we are looking at probability and the concept of probability. Okay, and we'll also be looking at probability distribution. Okay, in our first section, which is today's lecture, we are looking at the fundamental concept of probability. Just a minute. So we are looking at the fundamental concept of probability and to also understand the difference between discrete and continuous random variables. Okay, good. Yeah, so specifically, we are looking at the fundamental laws. We are looking at discrete random variables, looking at what a probability mass function is. We'll also be looking at the continuous random variables, okay, which we will look at the probability density function as the PDFs, the cumulative distribution, and then the properties of probability distributions like the mean and the variance of the random variable. Okay, now to start off, experiments for us as scientists, okay? We conduct a number of experiments, okay, as scientists, and every experiment generates different, or let me say, outcomes, okay? And for the same experiment which you conduct, after conducting it a number of times, you realize that your measurements or your outcomes may be slightly or different. Okay, so for example, you are in the electrical lab, you're conducting an experiment on the current flowing through a circuit. Okay, now as you're measuring the current for the same setup, you eventually realize that the current will the values of the current will slightly differ. Okay, aha. So, and this is due to a number of reasons. Sometimes one possible reason is the generation of heat, okay, within the circuit, okay, due to the resistance of the material, or let's say the resistance of the wire. So after a while, heat will be generated, resistance will go up, and then the current will also vary, okay? So what we are saying is in every experiment, we have inputs, okay? And then once we put in the input, we expect a result or an output. But within the process, in the process of observing the experiments, there are factors which we can control and factors which cannot be controlled by the experimenter, okay? There are certain factors which can be controlled, other factors cannot be controlled. So we have controllable variables and we also have the noise variables, okay? Yeah, so we're saying that an experiment that can result in different outcomes, okay, even can result in different outcomes, even though it is repeated in the same manner every time, is called a random experiment. And because experiments are random by nature, then it means that there is a certain chance of some kind of outcome, okay, occurring. There is a chance that a certain outcome will occur. That is the more reason why we need to look at the concept of probability distributions, okay? Yeah, there is a chance. So if you are standing at a bus stop expecting a bus, okay, there is a chance that the bus will show up after the first two buses, or there is a chance that the moment you get there, you're going to get a bus to your destination. Okay, good. Now there are some few terminologies we need to understand. Okay, the first one is the concept of sample space. Okay, a sample space, okay, is the set of all possible outcomes. We are here is a set of all possible outcomes of a statistical experiment, okay? So all the possible outcomes of any experiment, okay, when we put them together in a set, is referred to as the sample space, okay? And then each possible outcome or each outcome in the experiment, okay, is called what? An element or a member or a sample point, okay? Member, an element, or a sample point. So an example of an experiment is the roll of a die. If we roll a die has 6 faces, okay, from 1 to 6, okay? So in the process of rolling the die, there are 6 possible outcomes. We are not saying that they all occur at once. We are saying they are possible. It is possible any of them could show up. So the set of all possible outcomes, which is the sample space, is going to be what? The set 1 to 6, okay? At times too, we denote the sample space as what? As omega here, okay? So instead of S, we can use omega as we see over here. Then, yeah, there's another example. It says, in the toss of 2 coins, if we should toss 2 coins, we have this coin and then we have that coin. If we should toss them, we expect 2 outcomes at a time, okay? But what kind of outcomes are we looking at? It's possible we can have the head, okay, on the face of one and the head on the face of the second one, or we could have a head here, whereas we have a tail here, okay? And we can also have a tail on this face, a head here, okay? Or a tail on this side and a tail on this side, okay? So these are the possible outcomes: head, 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 tail, tail, head, and tail, tail. So we say that the sample space is given by what we observe here. Okay, let's go on to the next point. Yeah, now the next terminology we need to understand is the concept an event. An event is simply a subset of the sample space, okay, in a random experiment. So, and usually we are interested in that word, particular subset, okay? So for example, the event of observing an even number in the roll of a die. The roll of the die, we have 6 possible outcomes, but because we are interested in what? Observing an even number, okay? Yeah, the event is an even number in the roll of a die. So this is going to be the set of those what? Even numbers, which is a subset of the sample space. Okay, so E is a subset of the sample space. Good. Now another example is observing at least a head in the toss of 2 coins. Okay, here we have head, 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 tail, tail, head. Okay, which is also a subset of what? The sample space, which have 4 possible what? Outcomes. Now, the probability of an event, E, defined as P of E, okay? So when we see this notation, this is the probability of the event, okay? Is defined as the number of outcomes in the event, okay? Number of outcomes in the event over the number of outcomes in the sample space, okay? So the probability of an event is the number of outcomes in the event over the number of outcomes in the sample space. Very well. So take note of that. Yeah, next we look at some few properties. Okay, now there are certain things we need to know. The probability of every set of possible events lies between 0 and 1 inclusive, okay? So the probability of any event, E, okay, is between what? Is between 1 and what? And 0, okay? Is between 1 and 0. So if the probability of the event is 0, then it means that there is no chance of the event what? Occurring. And then when the probability is 1, then it means that we are sure that that event will occur. Okay. Now next we are saying that the probability of the whole set of outcomes is always 1, okay? So as an example, or in other words, the sum of all probabilities is equal to 1. So when, as an example, the probability of the various outcomes, okay, the sum of the various probabilities in the toss of a die will be equal to what? Will be equal to 1, okay? Good, okay. Now, if A and B, just a minute, please. Let me. Sorry. If A and B are 2 events with no common outcomes, then the probability of their union is the sum of their probabilities, okay? So if we have event E1 and then event E2, okay, equals to 6, and then event E1 is a outcome 1, then the probability, okay, of the union of the event is equals to the sum of their probability. So the probability of E1 observing a 1 or a 6 is equals to the probability of observing a 1 plus the probability of observing a 6. Yeah, then another thing we have to know is a complementary event, okay, which we know from set. So the probability of an event A is equals to 1 minus the probability of not A. Okay, yeah. So that is the probability that A will not happen is just 1 minus the probability that A will happen. I think we know this from set theory. Okay. Then we come on to joint events. Okay. Now, when we say joint event, joint just mean you have 2 or more. Okay. So, for example, we want to find the probability of observing a 1 and a 6. Okay. They are joint events. A rainy and a sunny day. Okay. These are our joint events. Now, the first operation, which we call the addition rule, okay, or the addition of events, says that the probability of 2 events, okay, in conjunction, it is the probability of both events together. So the probability of P or B is defined as P of A plus P of B minus the P of A intersection B. We call this the addition, okay, the addition rule, okay, the addition rule. Okay, so this is the addition rule. Good. Yeah, so anytime we have, you're finding the probability of A or B is simply P of A plus P of B, okay, minus P of A intersection B. Good. I hope you've taken note of that. Very well. But under certain circumstance, this, okay, this final term here will be 0 if the 2 outcomes are mutually exclusive, okay? So if the 2 outcomes are mutually exclusive, then we have P of A intersection B, okay, will be equal to what? Will be equal to 0, okay? When do we say that 2 events are mutually exclusive? Mutual exclusive means the 2 events cannot occur together. Okay, so if, example, if I ask you to find in a box, find the probability of observing a ball that is red and green. Yeah, and by definition, this is going to be the probability of observing a red ball plus the probability of observing a blue ball minus the probability of observing a red and a blue ball. So if all the balls in the box are unicolor, okay, they have just one color, then it's not possible to select a ball which will have a red and a green color, okay? So in that case, we say that the event A intersection B, A and B are mutually exclusive. So it means that A intersection B will be an empty set, which also means that their probability will be equal to what? 0. Okay. Then we have the next rule, the independent event, which is as a result of the conditional probability. We'll come to that. We'll come and show that very soon. Okay, so P of A intersection B is also equal to P of A times P of B, okay, for independent events. But this is derived from the conditional probability. We'll derive that very soon. Okay. Now, we want to try some examples on the independent rule. I hope you took note of the rule, okay? So P of A intersection B is equals to P of A times P of B. Take note of that for independent events. Okay, so let's try an example on independent event. Okay, let's do one for the first example. That's addition rule. Okay, so for addition rule, we say in a certain study, pupils are classified as overweight underweight or having normal weight. The probability that a pupil is underweight is 0.3. The probability that a pupil is normal weight is 0.5. And the probability that a pupil is overweight is 0.2. Find the probability that a pupil selected at random is either overweight or underweight. Okay, good. So we can define the events as what? That's A as being overweight and then B as being what? Underweight. Okay, very good. And then next we have the probability of being overweight to be 0.2. That's the probability of A to be 0.2, whereas the probability of B is 0.3. That's the probability of being underweight. Okay, so since we've been told to find the probability that the student is either overweight, okay, either overweight or underweight, that will be the probability of A or B, which is going to be, ideally, that would have been P of A plus P of B minus the probability of what? P of A intersection what? Intersection B. Okay, but you see, you cannot select a student who is overweight and underweight at the same time, because overweight and underweight are mutually exclusive events, which means that A intersection B is what? It's a null set. Okay, they are mutually exclusive, so there's not going to be any person who is overweight and underweight at the same time in the class. Okay, hence the probability is equal to what? 0. Okay, that is why we are left with what? P of A plus P of B. Okay, then we put in the values, which will be 0.2 plus 0.3, which is equal to what? 0.5. So that is for the addition rule. Okay, now let's try any question on addition rule. Any question on the addition rule? I'm moving on. Any question on addition rule? Okay. In the absence of any question, we want to take the next example, which relates to the independence. Okay. So for independence, we said P of A intersection B is equals to P of A times P of B. Okay. So we take an example. We have three balls, 1, 2, 3 in a box. Okay, and they have equal probability of being selected. So we are looking at two different cases. Okay, the first case is we are looking at the independent case, and the case 2 will be the dependent case. Okay, trying to understand the concept of independence. So it says that the case 1, draw with replacement of the ball. The second draw is independent of the first. So if I pick the first guy out, okay, so I pick it out on the first drawing and then replace it before I pick another person out. So it says that find the probability of drawing E1 and E2, okay? Now, because our formula says what? That is the probability of A and B is equals to the probability of A times B. Okay, so this is going to be the probability of what? E1. The probability of E1 intersection E2 will be the probability of what? E1 times the probability of E2. Okay, very good. Now, in demonstrating this, we said that the probability of E1, if we are drawing E1, that is E1. So we took it out And at the time we're taking it out, that will be 1 out of a total of 3. So that is the probability. Okay, times, because we will replace it before taking E2 out. At the time of selecting E2, there are still 3 balls in the box. So that will also be 1 over 3. Okay, so at the end of the day, that is going to give us what? 1 over 9. And 1 over 9 is just the probability for each selecting what? Each ball. Okay, this is 1 over 3. This is 1 over 3. Good. Well, however, in case 2, when we draw without replacement, then the second ball becomes dependent. The second ball will become dependent on the first one. Okay, in the sense that when we select the first ball, okay, before we selected it, there were 3 balls, so we are going to have the probability of E1 to be what? 1 over 3. But because we've already drawn this ball out of the box, there are only 2 left, okay? So the probability of selecting E2 becomes what? 1 over 2, okay? So you see that at the end of the day, the probability will be 1 over 6 in the case where the second event depends on the first, okay? So in a dependent scenario where the 2 events are dependent, okay, then the probability of E1 and E2 is not equal to the probability of E1 times E2, like in the case of what? The independence. Okay, so in a dependent scenario, the probability is not equal to the probability in the independent what? Event. Okay, now let's take some further explanation. That brings us to the concept of conditional probability. Good. So we are saying that the conditional probability P of A given B, okay, that is A given that B has occurred. So like we just looked at selecting E2. Selecting E2 depended on E1 already being what? Selected. So the probability of E2 depended on the fact that E1 has been selected, okay, prior to its experiment. So we are saying that the probability of A1 given, the probability of A given what? B is the probability of the event A given that the occurrence of some other event B, okay, and is defined as what? P of A given B is defined as P of A intersection B over what? P of B. Okay, good. So that is what we are saying. So this simply means that we can also write, I'm just going to cross multiply. Okay, so let me do this. P of B. Okay, and then this side to P of B. So this is P of B. Okay, so when we cancel out, this will cancel out this way. So which means that by the conditional probability rule, we can say that P of A, okay, intersection B, okay, in the case of dependency, it's supposed to be what? P of A given B, okay, times P of what? P of B, okay, good. So what we are saying here is, please follow carefully. I'm saying follow carefully because you see, on the alphabet, you expect B to come after A. But in this notation here, we are saying that probability of A given that B has occurred. So B has already taken place. Okay. So A given that B has occurred is going to be equal to what? The probability of A and B occurring over the probability of what? B. This is the definition here. Okay. Now, per our cross multiplication we just did, we've also come to the second equation, which says that the probability of A and B occurring. So if you want to find the probability of A and B occurring, it is the probability that B occurred, that is the first event. B is the first event. Okay, so the probability that B has occurred times the probability that A occurs given that B has what? Occurred. Okay, class, I hope that is clear with you.
Yes, sir.
Yes, sir.
Very good. Okay, so that, just a minute, let me erase this portion. Very good. So based on this, okay, if we have a dependent scenario, then it means that you find your probability of A and B using this equation. But in the case where A does not depend on B, then we say that if A and B are independent, okay, then A given B is just what? Probability of A. The same way B given A is also independent, B is independent of A. So that will also be the probability of what? Of B. Okay, which means that then this term is going to change and we'll get the previous independent formula which we saw, which is A intersection B, okay, is equal to what? Is equal to P of A times P of what? Probability of what? Of B. That is how the multiplication rule was derived. So in the case of what? Independence, okay, then we get the multiplication rule for independent event, which is P of A times P of B. Okay, very well. Okay, so we call P of A or P of B the prior distribution, okay, whilst P of A given B is called what? The posterior distribution. Okay, so P of A, and then we have P of A given B as the posterior. Okay, very good. Now, I think that's a similar example. Let's look at that. So what we are saying is, if you want the probability of A and B, is just the probability A given B is just the probability of A and B over the probability of what? B. Okay. So in the similar example which we looked at, if we want to find, okay, the conditional probability, finding the probability of E1, given that E2 has occurred, okay, E1 given that E2 has occurred, is going to be defined as what? P of what? P of E1 and E2 over P of what? E2, the probability of E2, okay? So P of E1 and E2, okay, per our definition, is going to be 1 over 3 times 1 over 3 over what? 1 over 3, which gives us a total of what? 1 over 3, okay? This is in the case of what? Replacement, don't forget, okay? Then in the case of, in case 2, where we are drawing without replacement, good, we said that E2, okay, will depend on E1. So it's going to be 1 over 3 times 1 over 2 over 1 over 3 by the conditional probability, which gives us what? Which will give us half, okay? So the probability of E1 given E2 in a drawing without replacement will give us what? 1 over 2. Very well. Then we also have one other example up here, okay, which I want you to look at, okay, in disease modeling. So here we have, it says in a certain population, 10% of people are classified as high risk for a heart attack. Okay, 2 people are randomly selected from this population. What is the probability that exactly one of the 2 is high risk? Okay, good. So what you do first is to define your sets. We are saying that H is for high risk, N is for not at risk, and the probability of a high risk is what? 10%, which is 0.1. And the probability of not at risk should be 1 minus, okay, 0.1, which is 0.9. So the probability of observing somebody who is high risk, okay, exactly one who is high risk, means that one of the 2 people selected, okay, is not at risk. But the question is it the first or the second? Okay, so which means that the probability